All right, welcome everyone. We have Benjamin Bumpus to talk us through how we can chop things up to decide things fast, or also compositional algorithms on compositional data.
Thank you. Can you all hear me? All right. So, well, first of all, I want to start off by saying that it's a pleasure to be here. It's always fun to hang out with ACT people. I've come to category theory from a different discipline, and I've found that this is a really friendly community, and so I just wanted to say thanks to everybody. There's a lot of genuinely nice people. So that's always what I'm about. So today I'm going to be talking about how you chop something up so you can decide stuff fast. And this is joint work with Ernst Haltas, who's at the University of Mainz, James Fairbanks, he's my boss, Daniel Rosiak, who sat right there. And this is in turn based on joint work with Jade Master, who's at University of Strathclyde, and Zoltan Kokshish, who's at University of New South Wales. Also, throughout this talk, I'm going to be mentioning some things about sheaves, but barely nothing, because I don't assume that everybody knows things about sheaf theory. So if you're interested, check out the blog, read Daniel's book, and you will become a sheaf theorist. All right, so Abramsky and Shaw point out that there's a remarkable divide in theoretical computer science, that there's these two communities that they call the structure community and the power community. The structure community is the one that's interested in semantics and compositionality, and the power community is instead interested in expressiveness and complexity. So why is this divide remarkable? Well, it's remarkable, they say, because the communities are almost disjoint. They're using completely different technical tools, different mathematics, different kinds of language to speak about their problem. And of course, they're asking different questions.
Excuse me.
Yeah.
The slides aren't visible for the online people.
Oh no.
There seems to be something in the way, or the screen's not being shared.
Is it being shared now?
Yeah, that looks good.
Are we recording? All right, so, well, the point is that you've got these two almost disjoint research communities. And I suppose part of my perspective coming from complexity theory is that although it's true that compositionality has never been something that we've studied in complexity theory in a formal sense, it's always been there. So in graph theory, probably the biggest result in the past 100 years in graph theory is Robertson and Seymour's graph minors project. This spanned 23 papers to prove Wagner's conjecture. And the key technical tool for them are these things called tree decompositions, which are ways of chopping graphs up in a recursive way. So it's compositional structure of the graphs. And similarly, in complexity theory, or in modern complexity theory, aka parametrized complexity theory, one of the prime things that people like to talk about are compositional algorithms, where you take solutions joined on small pieces and try to put them together to find solutions on the whole. So this talk is about taking the structure community and the power community and letting them talk to each other somehow. So how do we do this? We're going to take three forms of compositionality and use category theory to kind of blend them together into a wonderful soup. So the structural compositionality that I'm thinking about is the one that's inspired from graph theory, where we really want to chop things up and glue them together. The representational compositionality that comes from topologies is Sheaves. And then I'm going to be thinking of dynamic programming as the notion of algorithmic compositionality. So our main result is to take category theory and make all these things talk to each other and more. And our main algorithmic theorem says that every time you give me a problem that you can write down as a sheaf. This is where I'm waving my hands. Then this problem admits an algorithm which is recursive or compositional, but it's not just any recursive compositional algorithm, it's also fast. And by fast, I mean that it runs in time that grows linearly with the number of constituent pieces that you use to build your object, and boundedly in terms of the internal complexity of the pieces. Again, I'm hand waving. You can ask me more questions about this later. But okay, let's try to unpack these things a little bit. Now, given the time, I'm not going to go into details and turn anybody into a sheaf theorist, but so get ready for pictures. Okay, so let's start with sheaves and decompositions. So what's a sheaf? So a sheaf is a way of taking a space or something that's kind of space-like and attaching some data in such a way that you have restrictions between data. So if I have data defined on the whole thing, I can restrict it to data defined on the little bits and so forth. And you want to do this in such a way that when I have two bits of data that sort of match or agree on their shared domain, then I can lift this uniquely to data defined on the gluing. So the whole point of this exceedingly hand-wavy business is I just want you to be able to ask two questions. The first is, how do we give an arbitrary category, which is the cat, some sort of topological flavor, or enough of a topological flavor so that we can start talking about sheaves defined on this thing? And the second question is, so the sheaves, I've hand-waved, they are giving you a way of talking about compositionality of some data that I'm attaching to some space. But I'm also trying to build spaces in a compositional way. So I want these two forms of compositionality to talk to each other well. So the answer to the first question is thanks to another bald person. So there's this, this notion of a Grothendieck topology. It allows you to have just enough structure on a category to start talking about sheaves. I'm a huge fan. Daniel is converting me more and more to becoming a sheaf theorist. One day I'll grow up too. And the second question is, like, okay, that's cool, but like, so we have this Grothendieck topology. Can we do something useful with this? And it turns out that we can think of diagrams as yielding, again, there's another slide for this later, a Grothendieck topology on categories that have enough structure, and these categories are adhesive categories. All right, so I mentioned diagrams. Why do we care about this? So I like to think about a decomposition or compositional structure for some object in a category as just being displayed by some diagram and me taking the colimit of this diagram and building the thing. So in this talk, I'm going to be always, whoops, fascinating. Okay, something's out of order. But in this talk, I'm going to be thinking always that the category is going to be adhesive, and I want these diagrams to be of monomorphisms, so that they're indexed by a finite category. This finite category has all monos, and the diagram has to preserve them. Now I have to remember the strange order, but okay. So the point is that when C is adhesive and we have sufficient colimits, then these diagrams of monos define this Grothendieck topology on the category. And the practical thing that I'm saying is that this lets us have a topology with respect to which we can define sheaves, so that the compositional structure of the sheaves matches the compositional structure, or at least plays nicely with the compositional structure of how we're building our objects. All right. So for algorithmic reasons, and for other reasons which I can tell you about later, but mostly algorithmic is a good intuition, instead of using just any old diagram as representing a decomposition of some object, we want to think about a special class of diagrams. And a special class of diagrams are things that look like this. So they're called structured decompositions. I wrote about these with Jade Master and Zoltan Kalkshish. And they're essentially generalized graphs. So whereas a graph has a set of vertices and a set of edges, a structured decomposition has a collection of objects of some category and a collection of generalized relations, so spans between the vertex objects. So more formally, we write diagrams like this, and I should thank Evan Patterson for opening my eyes to a better way of writing these down. So the point is, you pick some category C, and this is the category in which you want to value your structured decomposition. And then you'll have a diagram that takes a graph G turns it into a category via Grothendieck construction. And this Grothendieck construction on the graph G, if G is viewed as a C-set, is just making a graph where I have a vertex, well, it's a category where I have an object for each edge, an object for each vertex, and a span from the edge to its source and sink. So structure decompositions assemble into a category. You have morphisms of structure decompositions are just morphisms of diagrams. In fact, this is a subcategory of the category of diagrams in C. All right, so now we can start talking about the algorithm. So okay, first of all, how do you talk about a computational problem as a sheaf? So first, let's try to think about computational problems as functors. So I'm going to take a functor that's just going to attach to each object of some category as the solution space to the problem I want to think about. And to me, I think that it's kind of like a very bad thing in complexity theory that people define computational problems without first defining the solution space and then defining the family of problems that comes from that. I think this is the right way of doing it. So here's an example. So you say you want to do k-coloring of a graph. So you start with the category of graphs and monomorphisms, and you take each graph to the set of proper k-colorings of the graph, where a proper k-coloring is you color each vertex with one of k colors in such a way that no edge is monochromatic, i.e. no edge joins two vertices of the same color. Another example could be the vertex cover problem. So this is another standard. It's one of Karp's 21 NP-hard problems that sort of started complexity theory. So you want to take a graph and you want to map it to the set of all the vertex subsets of size at most k, such that when each of these vertices hit all the edges in the graph, or equivalently, if I remove those vertices from the graph, I get an edgeless graph. So these are classical NP-hard problems, and we're living in this realm of NP-hard problems because we want to find the whole point of modern complexity theory or parameterized complexity theory is that although a problem might be NP-hard in general, you can expect there to be efficient solutions if you restrict the class of inputs you want to play on. So you might have linear time algorithms for some problem on a restricted class. So that's what we're aiming for. So okay, by the way, I'm writing my contravariant functors kind of funny because I like it. So I don't know, psychology is involved. So okay, I told you have a solution space, and there's many things you might want to do with the solution space, right? So the decision problem is deciding whether the solution space is empty or not. An optimization problem is deciding whether there's something in the solution space that satisfies whatever. So in this talk and in the paper, we only think about decision problems. And so how do you make a decision problem? Well, you start off with your functor f, which is assigning your solution space, and you compose it with this decision functor, which just maps a set to bottom if and only if it's empty. And so a second ago, I told you that you can construct categories of structure decompositions, and exactly in the same way as you can build categories of diagrams functorially, you can also do this for categories of structure decompositions. There's this functor, this curly d, which takes a category to the structure decompositions that are valued in that thing. So we can do the obvious thing, which is lift this functor f, or solution space functor, to a functor between the category dc, which is going to give you the category of decompositions of the inputs to my problem. And d of f is the same as taking f, and suppose you have some oracle that's computing f, or think of computing f by brute force. And now that's the same, this d of f is taking all the constituent parts of this diagram, hitting it with this oracle, and now I have shipped this over to a structured decomposition of the solution space of my problem. Now, I mentioned sheaves, and the sheafy part is very important, because when f is a sheaf, this thing commutes. What does this mean? So the Grothendieck of decomp is just a fancy way for having a category where I have, as objects, pairs, where I have some data and a decomposition of that data. And I've got two maps I can. So the commutativity of this is telling me that I can either take the first path, which corresponds to taking my data in the decomposition, burning the decomposition, brute forcing my solution when I go across f, and then deciding the problem, just checking if the whole solution space is empty or not. And the bottom path corresponds to taking my data in the decomposition. This time I throw the undecomposed data out. I compute locally on each one of the constituent parts of the data. I have a decomposition of the solution space, and now because F is a sheaf, I can combine a decomposition of the solution space and, thinking the word in Italian, whatever, I can do this well to go up into a solution space of the whole, and then I can just check whether the solution space in the whole thing is empty or not. So far, or at least when I started being in this field, I would tell this to people and they'd be like, oh, that's cool, that's a compositional algorithm. And it's really funny because coming from complexity theory, I was like, this is garbage. Because the point is that I'm computing the entire solution space. This is incredibly slow. Once I've written down the solution space at the top, I've already lost. Okay, so what can we do? Well, hey, D is functorial, so let's do it again. So, okay, what does that mean? So now I have this commutative, whatever shape that is on the left, and I can, so D of dec up is looking at each one of the bits of my decomposed solution space, and I ask, is it empty? Yes, no. And I have a decomposition of booleans, and then I combine those. So a note on the combination. Because of all the ops, things might not look as they appear. So colimits, for example, of solution spaces are actually limits and sets, right? So if that matches your intuition better, again, this is my psychological problem. But speaking of which, this thing doesn't commute. And if you want to convince yourself, imagine taking an odd cycle, a 5 cycle, for example, and writing it as a push-out of 2 paths, and now running this idea for checking if this 5 cycle is too colorable or not. But the whole point of the paper is that we can make this commute by first finding this endofunctor A on the category of structured decompositions of the solution spaces. What's really nice about this, well, there's a variety of things that are very nice about this. So first of all, this endofunctor works in the sense that it makes this diagram commute. But it's not just any endofunctor, it's kind of a canonical one, and it arises from an adjunction, this constant colimit adjunction you might know between a category and a category of diagrams valued in that category. So you can use this adjunction to figure out what A should be. And perhaps I can scribble later to talk about that. The second thing that's really nice about this is that if I just come to you and promise you that I can compute A efficiently, which we prove this in the paper, but if I promise you I can compute A efficiently, then you can see the running time of the whole algorithm already just by staring at the diagram. Why is this? Well, because, assume that I'm doing F by brute force. Then D of F is just brute force on chunks of data. And if I know that my input comes from a class where the chunks of data are bounded in size somehow, then now my running time is a constant, right? It's a big constant on these pieces, but it's a constant. And then I've done this big constant linear times, so that's still good. That's what D of F is doing. I've promised you I can do A quickly. Now D of dec up is just checking linear number of times whether some sets are empty. Again, this is fast. And then I'm just combining these booleans. So I think this is a really good thing. And like James was talking about the aesthetics of category theory, and I think that there's something really profound about that, because I think that in searching for something that is aesthetically right, it also clarifies the kind of way in which we should set up our algorithmic tasks. For example, in the parameterized complexity community, there's a big group of people who are interested in asking the question, well, actually, if you give me a decomposed graph that's built as a colimit of lots of pieces, it's not so much the size of the pieces that matters, but it's their internal complexity. If each piece has a small solution space, despite maybe being big, and I can compute that solution space relatively fast, then it doesn't matter that the piece is big. Now this is a realization that parameterized complexity has been around since the 80s, and only now people are starting to think about this, but for us it's obvious. It's obvious for a variety of reasons. First of all, we don't necessarily know how to attach a notion of size to objects of a category. So when we write down our running time bounds, we give them in terms of the size of the solution spaces, because those are sets. And we have nice ways to think about that. And second of all, that realization makes it obvious that it's not the size of the thing that you're computing on, it's its internal complexity, and we need to have good ways of talking about that. Right. So anyway, just to conclude, there's a few directions for future work are sometimes presheaves are not sheaves, and we get sad. What to do? Second thing is, I've told you that, like, well, the whole point is that we want to have compositional structure in the objects, but we want to know something about the compositional structure. So you want to have a decomposition, but you want the pieces to be nice. So what if an object can't be decomposed with nice pieces? And then it'd be interesting to look at applications of this work. So please get in touch. Thanks a lot.
All right, let's do some questions here. Should I throw?
Thanks, fantastic talk. Great talk, Benjamin. I enjoyed it very much. So I'm actually someone that does vertex covers for a living. So can you just take me through a little bit of this? Because you're doing the decision problem to decide, for example, if a billion-edge graph has a 1 million size vertex cover.
Yeah.
So you're going to do your sheaf decomposition. And so it seems to me you're maybe faced with a kind of a knapsack problem where you're counting the size of the vertex covers on subgraphs, and you have to kind of add them up. Can you just sort of explain how that works?
Yeah, so I should make a caveat. So vertex cover is one of those problems that is a pre-sheaf and not a sheaf, and it's sad. But we are currently working on that, and I am hopeful that we'll be able to turn it into a sheaf. Or, well, let me put it this way. The parameterized complexity literature knows how to do this. We don't know how to write it down as a sheaf yet, but that's an us problem, not a, yeah. So coloring is maybe a better example. So say you want to do 3 coloring. What you're doing is, imagine you built a graph as 2 pushouts, right? So in a path. Right? So and we're doing 3 coloring. So I enumerate all of the 3 colorings in the first chunk. I enumerate all the 3 colorings in the second and the third. And now I check whether the 3 colorings agree between the first 2, I call them bags, right? And I do this by projecting onto their common intersection. And then once I've computed all the 3 colorings that can be matched together, I project them back onto these initial parts. Now what I don't want to do is keep around the 3 colorings for the push out of this first push out. Because if I do that, my solution spaces grow. It's a very bad idea. What I want to do is have solution spaces that are always bounded in the size of the original local solution spaces, but I want to filter out from those the bad things. And in fact, that's what the monad of the adjunction is doing. So remember, you're taking colimits and set up, so it's actually limits and set. So you've got this diagram of cospans now, because I've opt everything. And I'm taking a limit of this thing. And now what I'm actually doing, what this functor A is doing, is that it takes my decomposition and maps it to a decomposition, which is given by taking the limit object and projecting it into each one of the constituent parts and keeping just the image. So now, I've replaced it with a bunch of sets that are all subsets of the original ones, but they have the property that I'll be a no instance if and only if I have an empty bag, an empty set in there.
Thanks, Ben. So I was wondering whether there are any sort of heuristics you can use to know whether a given problem might satisfy the sheaf condition, or whether that's something you just kind of need to think really hard about every time.
Well, right now, we're working on a general way for doing that. So my suspicion is that if your problem is, maybe that's not a helpful answer, but my suspicion is that if your problem is expressible in monadic second-order logic, then it should always be a sheaf. This is because there is a deep theorem that says that such problems are always efficiently solvable on graphs that are decomposable. The question of how to turn that into a sheaf statement is kind of open, although we're currently working on similar things. Tyler is here, and Tomasz Jakel and Gabriel Goren, that we're all kind of thinking about this right now.
Cool, thanks.
The fact that Purcell's theorem is famous says that that's the right answer. The method should produce the answer that people got once.
Well, no, it's just that it seems to be the right class of problems, right? That should be gluable.
Thanks for the talk. When you're doing decomposition, especially when you have very large graphs, let us say, are there rules for decomposition you're following? Because the way you decompose is going to affect your computational complexity.
So you're usually interested in a decomposition that has a shape that's a tree. So in these decompositions, our algorithm is very fast. one thing that we do new compared to the standard complexity theory literature is that we give our algorithm even when the decompositions are not trees, but the algorithm gets progressively worse the further away from a tree you get, in the sense that the number of vertices you have to remove to turn your graph into a sheaf, like the shape into a tree. And so there's the issue of like, if you give me data that's not decomposed, now you have to compute the decomposition. This is NP hard on graphs. Although we know that there are fast algorithms to do this anyway, if you suspect that, well, fast in the sense, parameterized by the thing you're trying to solve, so by the tree width. We can talk about this more. But James taught me that that's kind of the wrong way to think about it, in the sense that in practice, or like if you're using all the software from Algebraic Julia and you get modelers or people who are generating the data to build it compositionally, you got nothing to compute. That seems like the better answer to me. So, yeah.
Okay, thank you everyone for these questions. Let's thank our speaker one more time.